Davis-Beast Plan, 3/16 of an inch from disaster, corrosion mechanisms, and problem discovery. February 27, 2002, signs of the single worst nuclear power accident since 3 Mile Island were discovered at the Davis-Beast plant, pressurized water in Oak Harbor, Ohio. The story starts at the Oconee Nuclear Power Station in South Carolina in 2001, where through-wall circumferential cracking was discovered, and they thought this was caused by primary water stress corrosion cracking. The NRC ordered all plants of this design to shut down and inspect by December 31, 2001. The Davis-Beast plant negotiated to extend the date of this shutdown until February 16, 2002. Shortly after this shutdown was conducted, ultrasonic testing revealed that 3 control rod drive mechanisms had through-wall cracking and leakage. By March 8th, the Davis-Beast plant admitted publicly to a large metal loss. A hole in the reactor vessel was formed that was about the size of a football, and the only barrier between primary coolant was a stainless steel cladding that was 3/16 of an inch thick, that was not designed to withhold the rated pressure of the Davis-Beast plant. In this presentation, I'll discuss primary water stress corrosion cracking and boric acid corrosion, why we add boric acid to reactors in the first place, and signs that occurred much earlier than the 2001 Oconee incident that there could be problems in the Davis-Beast containment housing. First corrosion of concern is primary water stress corrosion cracking. It's a complex corrosion process that is driven by many of the factors that inherently exist in a nuclear power plant, whether it is a boiling water reactor or a pressurized water reactor. The necessary preconditions are susceptible material, tensile stress, and aqueous environment, which we summarized in this table from the International Atomic Energy Advisory. It includes chemical compositions, flow conditions, and the loading of the material. As you can see, many of these factors are unavoidable, such as tensile stress, which is caused by the high pressures in the reactor vessel, and also the high temperature in a nuclear power plant, and the inevitable irradiation damage caused by continued operations. Unfortunately, the exact mechanisms of primary water stress corrosion cracking are not fully understood. What is understood is empirical data collected has given us these factors. Likely factors for the Davis-Beast plant include irradiation damage caused by plant age, as neutron bombardment displaces atoms from their crystalline structure, and the control rod drive mechanisms, which are a cold work component, which also make you more susceptible to primary water stress corrosion cracking. What this primary water stress corrosion cracking allowed to happen was the boric acid corrosion to take over. Boric acid corrosion can occur in several forms. The most common is general wastage. In order to have general wastage, you have to have iron or steel and an excess of monatomic hydrogen atoms. Any acid in excess can cause these ions, and wastage is not unique to boric acid. Boric acid is a weak acid, and other acids, such as hydrochloric acid, more aggressively attack the metal. Boric acid creates the hydrogen atoms by this reaction. These hydrogen atoms go on to remove electrons from the iron and steel, becoming neutral hydrogen with no charge. The iron loses its electrons in this process, becoming iron +2. This is what's called an oxidation reaction. This iron goes on to react with oxygen to produce iron oxide in this reaction. Iron oxide is also known as hematite or rust. This creation of rust degrades the metal, and it wears away at the metal's thickness. Factors that affect boric acid corrosion are pH, oxygen, temperature, flow, and impurities. Boric acid is not normally a concern within the primary fluid system. Most components in the primary complex are clad with stainless steel, which is resistant to boric acid corrosion. The primary fluid system is a closed system and is normally oxygen-free. Primary fluid systems are carefully chemically treated so that boric acid concentrations are maintained well below the levels that would be harmful to plant materials, and the pH of the fluid is usually maintained mildly alkaline, which is the ideal environment for plant materials. Boric acid becomes a concern when there are small leaks in the primary system from gaskets, flanges, nozzles, welds, and these primary water stress corrosion cracking sites that we discussed. For boric acid to be at its most damaging, the right conditions have to occur. a leak rate that is slow, so that the evaporation of coolant concentrates its boric acid, creating a more acidic solution. The ideal temperature for boric acid corrosion to occur is approximately 212 Fahrenheit, which has the highest known corrosion rates. When water leaks out of the closed primary system, it will absorb air from the oxygen, which is also another vital component of the corrosion process, which is why these leak sites are the most damaging. What is boric acid and why do we add it? Boric acid is a white, odorless powdered substance that is not flammable, combustible, or explosive, and has a low acute oral and dermal toxicity. This is from the Boric Acid Material Safety Data Sheet. It has many industry uses, included as use of pesticide and cosmetics. We're here to talk about using boric acid as reactivity control in pressurized water reactors. Boron is what's called a neutron poison. A neutron poison is any material that absorbs neutrons. This ability to absorb neutrons is measured in barns, which is near 10 to the minus 28 square meters, as expressed as microscopic cross-section of absorption, which simply put is a quantitative way of measuring a substance's ability to absorb neutrons. Boron is an excellent neutron poison. It has a microscopic cross-section of absorption of 3,843 barns, compared to another common element such as carbon, which has a microscopic cross-section of about 4.95 barns. Boric acid, often called soluble boron, or boron for short, is used as chemical shim in some nuclear power plants, or it is used to keep plants shut down when control rods are removed during maintenance. Due to the injection process, boric acid can only be used to compensate for slow changes in reactivity. So what happened at Davis Beast? What likely happened is as the plant aged, it became more susceptible to primary water stress corrosion cracking due to this neutron embrittlement. Cracks were formed and then propagated that went through the reactor vessel head. This created small leaks, often referred to as weepage. This allowed primary coolant to collect on the outside of the reactor vessel head. Due to high temperatures that exist on the reactor vessel head, the coolant quickly evaporated, leaving an ever more concentrated acid solution. This boric acid solution ate away at the exterior of the reactor vessel head until it was discovered in February 2002. The reason that a complete failure did not occur is that the stainless steel interior cladding is not susceptible to boric acid corrosion and remained intact after the carbon steel head had been eaten away. So what warning signs did we ignore? During the previous shutdown, on July 30th of 1999, iron oxide granules were found on radiation monitoring filters. On April 6, 2000, workers found large amounts of boric acid buildup, and they were reportedly lava-like extrusions from the reactor vessel head. On April 23, 2001, so many boric acid crystals had been accumulating on radiation monitoring filters that the filters need to be replaced significantly more frequently. All these signs pointed to a significant issue in the containment structure. In conclusion, the boric acid incident was caused by a synergistic attack on the reactor vessel head by two well-known corrosion processes: primary water stress corrosion cracking, boric acid corrosion. Multiple indications were available years in advance of the incursion, and no actions were taken to correct these errors.